So, good morning, everybody. It's time to start working really with images. Until now, we have only talked about what images are and that other people can produce data. Now, this is the first lecture where I'm going to really show what you can do with images. And the first step is about image enhancement. And let's see, I need to switch on that one. So first the thing is images are unfortunately rarely perfect. There is noise, there are artifacts, and to remove that we need different kinds of filters. And I'm going to show you some traditional ones and also some more advanced types of filters. Finally, if you modify your images, you have to know if you did it right, because you can't modify it too much, because then it's not showing the same thing as you expected it to. And that is what evaluation workflows is about. First step is we need always some of these modules again. And as I said, images or measurements actually are rarely perfect. And you would maybe expect that you have a perfect image, a cross-section, which is a circle, a little bit displaced. But when you put it through your acquisition system, first thing is what's happening is you get some blurring. You have optical transfer functions. What is also happening is you get noise, detector noise, maybe counting noise, etc. And you may also get artifacts, like in tomography, it's very common to have ring artifacts and line artifacts. Can also have streaks of different kinds. And when all this is combined, then you get an image like this instead. Okay, usually it should actually be black and white, but you see it better when I have this column up. And things that can affect image quality is, as I said, resolution, noise, also contrast is a thing. If the modality you use doesn't provide a contrast very well between different components you want to look at. For example, in the human body, you have bones towards tissue, that's high contrast. But if you want to see the difference in between organs, then the difference is very subtle, and that is the problem. Can also be that the illumination is inhomogeneous. That can be fixed by normalization. And on top of that, you can have a bunch of artifacts. In our processing chain, we have several steps. Usually you can't say, give it an image to the computer and say, okay, do something for me. But it's actually a recipe based on several steps. And the first one is acquisition. Then we have enhancement to clean out all the unwanted information from the images in order to make it possible for segmentation and other post-processing, preparing for the evaluation for your investigation. And noise and artifacts, that's something very generally is the unwanted information in the signal. And when I talk about noise, it's actually more precisely random contributions that to some extent obscure the information that you have in the images. If you have too low signal to noise ratio, a term where I will explain a little bit later, you don't see it. You don't see anything in the image. And that is what we want to get rid of. That the thing that hides your information. You have different types of noise. In this example here, we have spatially uncorrelated noise, which every pixel has its own noise distribution. There is event noise, could be some kind of speckle that comes in images, and you have structured noise, and that is when the noise distribution actually affects several pixels. And here you can see the difference between the Gaussian noise here. That's where very rapid changes. And this one, in the structured one, you can see that it's a bit smoother. And a practical example of what's happening is when you get this is, for one, already through the measurement. My special case is neutron imaging, where you have a neutron hitting the scintillator and it gives you a flare. And that flare is spread out within the scintillator. And the result is you get images looking like this. Another one is if you apply some kind of filter, you can have done something to the image, bring it from here to here, probably with higher signal to noise ratio, but you have this structure now in the noise. Typically, when you talk about noise, the first model you come across is the Gaussian noise. It's very easy to work with. It's additive, and that's usually the first model that people take to when they start doing talking about noise, because it's so easy to work with. Actually, one reason for it is the law of large numbers. If you have many observations, most distributions, they actually converge towards something that looks like the Gaussian distribution. So if you can afford to do many measurements, then you are safe within the Gaussian assumption. What is more relevant for imaging applications, where you have some kind of events that are coming in that you count, then that's actually the Poisson noise. And it's a bit skewed distribution, in particular for low counts. You can see here, this is the example of, I think that's the lambda 3 or something. And interesting thing about the Poisson noise is that the variance and the average is the same value. And yes, so that's an interesting fact about that distribution. But also, if you do many counts, you will have a shape that looks very much like the Gaussian. But what happens is that the position of it moves with the strength of the signal. So it's not completely, so every observation looks like a Gaussian, but it's sensitive to the intensity you work with. And here you have an example, just plotted a sine with the additive Gaussian noise. You can see that the noise amplitude here is essentially the same across the sine. If you do the same, add the same Poisson noise to the signal, you can see in this area here, where you have high amplitude, you get larger amplitude of the noise than you get here at the low amplitude. So also, if I extract it, it's a little bit difficult to compare now, because unfortunately the amplitude here in this area is lower. But that should be the same all over. And this one, they should have a higher amplitude in this region than you have in this region. Another type of noise, which is very common in measurement situations, is some kind of spot noise or salt and pepper noise. That is randomly distributed outliers throughout the image. And usually you say you have a percentage of spots distributed over the image. And the distribution, well, that's whatever model that can be. But in this case, I just took a uniform distribution, randomly distributed. And if it's over some threshold, it's get a black dot. And if it's over some other threshold, it gets a white dot. And that would look like something like this. Here we have, 2% outliers, 10%, and 20% outliers. And this is also something that you get in neutron imaging, but also in other modalities. I think in microscopy, I think it's also quite common to get these spots. And now we have just seen that we have different types of noise, but usually when you want to describe it, you want to have some kind of metric to describe what your noise is like. And that is what we often use is the signal to noise ratio, which is the average value of the image gray level and in a small region, and divided by the standard deviation of the same region. So this could look something like this. You have, in this case, I just measured here outside of this sample. And this is from a neutron image, and that is counting noise. So we have a Poisson model. And the interesting thing here is that if you take now the average of this region that I selected, divided by the standard deviation, you get number of items or counted events divided by the square root of counted events. So for Poisson noise, very special case, the signal to noise ratio is proportional to the square root of events that comes in. And here you can see in this example, this was an image taken at 50 milliseconds. And here I have one taken at 10 seconds. You can see already visually that there is a big difference between the two images in signal to noise ratio. And then in this sequence, I did many measurements. And you can see that it nicely follows this square root of n, or exposure time. Exposure time is proportional to number of events you count. And and the series I did here was kind of a logarithmic series. So I took 1 second, 2 seconds, 4 seconds, 8 seconds, and then I went, oh, no, I took 1, 2, 5, 10, 1, 10, 20, 50, and 100. So that was the kind of sequence I used. Then you span a larger parameter interval easier. And to create this, when you start working with it, there are several Python functions to support it. In the NumPy package, you have the random section, and here you have normal distribution, mu, sigma, and the size of the image you want to create. And the same goes for uniform and Poisson noise. I think there are some more noise models, but these are the most frequent one you use. And to compute statistics, you have NumPy mean. And actually, if you have a NumPy array, you can actually take the variable dot mean, and then you get the average value instead of doing NP mean variable. So that is, you can do it in 2 ways here. So now we know about noise, and the next step is how to remove it. And for that, we need some kind of filters. And a very general definition of what a filter is some kind of function, method, processing unit that enhances the information that you want to see and suppress the information that you don't want to see. And ideally, it shouldn't affect the information you want to see, or at least shouldn't modify it too much. And that is the goal of our filtering, that we want to see what we have measured. There are different types of filters, and in principle, they are characterized in what kind of information they want to suppress and amplify. And often we talk about here spatial frequencies. An image, so in a normal signal, you can see that you have low frequency information, high frequency information. So the squeaky things are high frequency and the bass tones are low frequency. The same thing applies to images. And if you have a low pass filter, that's a filter that focuses on amplifying the lower frequencies, then you can see here that if you apply that on this image where you have a combination of slow variations and rapid variations. And after applying a low-pass filter, you suppress all the rapid changes, and you can see nicely the smooth variations in the image. And that is ideal to suppress noise, because noise is usually rather rapid variations in the image. The other thing would be to use a high-pass filter. That's the opposite. So it suppresses all the slow variations and give us instead the rapid variations. So if you want to see only the noise, then that would be the filter type. Later, I will show what you can do more with a high-pass filter, because it's actually useful for more than extracting the noise itself. And typically, what we start with is the linear filters based on the convolution operation. And that is, we have two components. One is the image, that's the fx in this case. And then we have a filter kernel H. And that is a little matrix that you actually sweep over and convolve with the image information. And here you have two typical filter kernels that we use. One is actually a child with very many names. So it can be the mean filter, called the mean filter, a box filter, uniform filter. The idea is that all filter weights in this kernel have the same value. And then you divide by the number of elements. So it's actually, it computes the average value, local average value in the image. Another one is the Gauss filter. And here you can see from the shape of it that it's tapering off towards the further away you come from the filter center. And it's often confused that if you have Gauss noise, then you use a Gauss filter. Sure, you can do it, but they are not related. But it's a useful filter because it's actually centralizes the averaging towards the center of the pixel that you are focusing around. When I say centering, that's also an important point. You have to decide what is the insertion point of the filter convolution operation, because you could, in principle, insert the filter at this point and compute everything to the right of and below that point. That has the disadvantage that you actually shift the whole image by the size of the filter kernel. So what you normally want to do is first, you want to have an odd numbered filter kernel, the odd number in the elements, and you want to center it around the midpoint. Then you don't have any displacements of your filtered image. And here you can see what happens when we have different signal to noise ratio and apply a Gauss filter. Here you can, well, again, the light is not on our side, but you can probably see the concept that if you decrease the signal to noise ratio, you can see that the image information is really getting more and more obscured by the noise. And if you apply a Gauss filter now with sigma equal 1 and sigma equal 3, you can see that on the clean image, you can clearly see the blurring that this filter introduces, because you're all the time you're computing a local average, and that will have a smoothing effect also on the structures in the image. And if you apply that filter to decreasing signal to noise ratio, you can see that in this case, it actually did a decent job. Here it's no doubt. On this one as well, but here you can start seeing that there is some residual noise in the image. And in the worst case, it didn't help much to have sigma equal 1, but you can at least get rid of the noise if you have sigma equal 3, but you also lose all information essentially about the sample itself. So that is the balance when you start selecting a filter kernel, that you have to see how much do you destroy relevant information compared to how much you can suppress the noise. And very simply explaining how the convolution is computed. If you have a box filter, what is happening if you go around this central pixel, you extract all the neighboring pixels, compute the sum, divide by the 9, because we have 9 elements, and then you get a 3.7 from this region, and that is inserted into the pixel itself. So this is the operation that's happening. There are already implemented functions for you, so unless you find a joy in implementing your own convolution, you don't have to. They are already available in multiple packages for image processing and signal processing. One interesting thing is what's called Euclidean separability. There are quite many filters that you can split into several pieces. And what that is based on is that the commutative and associative laws, they apply to convolution. So you can, in principle, apply the convolution AB on C, or A convolution with B convolved C. That is the same result. And you can also change the order, and that's also fine. And this is something we can use for some symmetric kernels. And two of them are the box filter, which you can split up in one vertical part and one horizontal part. And same goes actually also for the Gauss filter, where you can split it up into, again, one horizontal part and one vertical part. Now you ask yourself maybe, why this mess? It's just mathematical playing around. But actually there is a reason. And that is, when you do it like this, for a small kernel like 3 by 3, doesn't make sense. But anyway, you can see here that you have 9 multiplications and 8 additions when you do this in the normal way. And if you use it the separable way, you have 6 multiplications and 4 additions. So you can see that there is a reduction in number of operations you do. If you have a 3-dimensional kernel, then you all of a sudden start seeing the benefit of it, because here you have 27 multiplications and 26 additions. And that is reduced to 9 multiplication and 6 additions. It gets even more extreme. Now I don't have the numbers in my head, but if you have a 3-dimensional kernel which is 5 by 5 by 5, then you have 125 multiplications, and I think it goes down to something like 25 multiplications instead. So there, if you go in 3D using larger kernels, it actually makes sense to think about this. Then, of course, there is some technical details that it actually costs to call these functions twice. So there's a little bit overhead, and that overhead you have to balance against the numerical benefit. That is something you have to explore for your images, that you have to do timings and see, does it make sense? Does it not? Sometimes it's already built in, this effect into the predefined filters, I believe, because there is not so much difference as I would expect. But it's good to know at least that if you have large kernels, then maybe you can speed up things by doing this. The median filter is another filter type, which is of low pass type, but it's not linear. Because what you're doing is you're extracting the same region here, but now you compute the local median instead. So you sort all the elements, take out the middle one, and place it here on the position of the pixel again. And that is pretty useful in many cases. I think this is something you better see on your own screen, is to show when you have spots in images, you have Gaussian noise. Oh, okay, that's the order. Okay, I got a bit confused, sorry. You have spots in the image, and you have Gaussian noise. And using a Gauss filter on spots, the effect is that you smear out the spots. So you will have somewhat lower amplitude of the spots, but they take up more space. So it's Gauss filter for spots is not very efficient. On the other hand, if you apply a median filter on spots, then they will probably be pretty well removed, because a spot is an outlier, and if you sort the local information, the outlier is always on the extremes of the little array, and in the middle you have the real information you want. If you apply Gauss filter to Gaussian noise, then you have a pretty good performance actually, and actually better, even if it's not visible here. The noise removal effect is better using a Gauss filter than a median filter. However, median filter is more gentle to edges. So if you have sharp edges in your image, then maybe median filter could be a better choice. And here is an example, again from neutron imaging, is that in neutron imaging we get always, yes?
I didn't understand why, if you have sharp edges, the median would be better. Wouldn't you have like more of an outline?
And no, the edge is, let's say you have, let's say the blocks like this, and on one side of the edge, it's lower than on the other side. Mm-hmm. And when the kernel is moving over, then in the beginning, it's dominating the low value. And of course, it gets the low value. And then if you come more on the other side of the edge at the high value, then the high value dominates. And then you have a sharp transition between the two levels in the image.
But because it's more constant.
Yes, because you have a large chunk of low values, you have a large chunk of high values. Okay. Yeah. That is the reason. And yeah, so this is a spot cleaning example. And we get a lot of these spots in the images. They can be single spots, they can be small streaks. And they also vary in intensity. And we want to get rid of them because they are really very annoying for quantification from the images, for segmentation. So you get a lot of misclassified information if you have these spots. So our possible solutions is one, to apply a low pass filter because it's actually also some kind of noise. The other way would be to apply a median filter. And what I'm going to show now is a little bit more complicated scheme that includes detecting the spots and then replace them by something else. And oops, that wasn't meant to happen. That was something I missed, apparently. Yeah, there was a sub slide, of course. Yeah, I think I'm safe. So back to the slide and next one. The algorithm I'm proposing here is that you have your original image with your median filter. And the next step is to subtract the median filtered from the original one. And the difference, what you see, is essentially the spots and some small noise outliers. And then you compute the absolute of this difference, and outliers are values that are greater than a certain threshold. Those you try to create some kind of replacement for, and the replacement is the local median filtered value. And if there is not, if it's below this threshold, of course, keep the original. And afterwards, you combine the two results into one, and then you have the clean data. Now you can maybe ask yourself, why do we want to do something that's complicated? Median filter takes the outliers. Yes and no. The thing is, when you have this original image and apply the box filter, you can see that, well, the spots, they actually come out as small blobs in the data. You have some general smoothing. The median filter removes the spots, but you can also see that there is an additional smoothing. And you want to maintain as much as you can of the image sharpness. And with this cleaning algorithm, you actually only remove the spots and leave the image as it was before. And if you look at the difference, which is something is recommended to do very often, when you do filtering, that you do an difference image of before and after, then you can see what the filter actually did to your data. And here you can see that, well, the box filter actually, yeah, it took out the noise, it took out something of the spots, but you can even see that you use the box filter because the footprint where you have the spots is actually also a box. The median filter takes noise and spots. And if you use this cleaning algorithm, you can see that it's only the spots that have been removed. And that was actually the goal of the whole thing. In ImageJ, which is a popular tool for looking at images, there are different ways to remove outliers. One is called despeckle. That is just a renaming of the median operation. Don't use that to remove spots. And then there is another operation called remove outliers, which is very similar to what I described here. And that is what I more recommend to work with if you do spot removal in ImageJ. Next type of filters is the high pass filter. Yes?
Could you please give a little bit more reasoning on why we shouldn't use the other?
You mean the normal median filter?
The despeckle.
The despeckle is a median.
Ah, okay.
Just plain and simple. It's just a renaming of the median. Quite stupid just to put it renaming it, because the median filter is about 2 menu steps away. So I don't know why they have done it. So the high pass filters have a little bit different weight configuration. We are now looking for high frequencies, and high frequencies are essentially the derivative information. So with a high pass filter, you can compute derivatives, and there are different ways of defining the derivatives. So this is a very simple one, just take the two neighbors. But as I said before, this is an even numbered sized kernel, and you will have a displacement if you use this one. And then there were a couple of guys, they came up with this configuration. First of all, it's a odd numbered, and to get that, they added a row of zeros in the middle. And also the choice of this -3, 3, 10, 3 has proven to be the best way to get also the direction of the gradient. If you do just once throughout, then you will be biased in the angle between x and y derivatives. And this one has proven to be the best one. Another operator, which is also very popular, is the Laplacian, where you have a center negative large value and surrounded by lower valued positive. Actually, this is the sum of the surroundings. Yet another, which is also very popular, which is the magnitude of the gradient. And both, let's see, Laplacian and magnitude of gradient, they are used very much to detect high frequency structures. And high frequency structures, what are they in the image? Any idea? So where do you have rapid changes? Edges, exactly. So what these filters are used for is to detect edges. And looking at this, you can see here, first we just look at the vertical edges and horizontal edges, each at a time. And here you can see the effect of applying the X direction. You can see all the vertical edges. And then you can also see the horizontal edges applying this filter. So you can separate it and identify which kind of edges you want to look at. Mostly, it's more relevant to look at the whole edge as such. So you want to see all the boundary boxes around the object. And here I show an example of Laplacian and Sobel filtering. Sobel is the magnitude. And what you can see in these images is that in the Laplacian case, you have both positive and negative values around the edges. Whereas on the Sobel filter, you only have positive values. Depending on which detection algorithm you're using, both can be useful. So for example, using the Laplacian, you know that you are coming from which side you are approaching. So if you're coming from high to low or from low to high, that you can see because of the sign change in a Laplacian. And with Sobel, well, you get the edges pretty well marked up. Not on my Beamer screen here, but on your own screens, you can probably see very nicely the boxes around here. Another thing where convolution filters are very important is in machine learning, because if you do machine learning to analyze images, what you do is building up so-called convolutional networks where the neural network is built up by very many convolution kernels that are applied to the images to provide weights that the learning algorithm is looking at. And looking at different features here, you can see that first of all, you have directions is one thing that you're looking at. Could be also corners that the filters are focusing on. And then on different scales, you can get to different places in the image. And afterwards, in the whole machine, everything is weighted together, and hopefully you can this network can learn something. And this particular example from NVIDIA detects that the image represents a sign, and it can also detect which speed limit it sets. So that is an example that convolutions are also used in a very large context for machine learning. So question is if we make a break now. No, I do the frequency space too, and then we take the break. I have already talked about frequencies, and the way we can work with images in frequency space is actually also very helpful. And that we need to do using the Fourier transform. And well, you have probably seen the Fourier transform before. In 1D is the typical thing you see in the math class, but you can actually expand it to any dimension you want to. And then you add different spatial frequencies in all directions, as you can see here. Whoops. And there is, of course, also an inverse transform. And this looks a bit ugly. It's not fun to compute. And thankfully, there are a lot of libraries doing fast Fourier transform for you. You have it in NumPy already. You have it also as separate packages in any language, programming language. So you don't have to implement the Fourier transform yourself. But what is done is using the so-called forced Fourier transform, because the Fourier transform operation itself is quite time-consuming to compute. It's complexity of the square of number of elements you compute. And the fast Fourier transform is n log n of the complexity. So you actually speed up things quite much. There are some practical things around the Fourier transform that you need to size your images in the right way. Must be multiple of 2, otherwise you have to do padding, but that's something you can live with actually. It's easily done. The Fourier transform, looking at some basic properties of it, is that if you add 2 signals, it's the same, and take the Fourier transform of it is the same as if you take the Fourier transform of each signal separately. So what you can see here in this example is we have signal 1 or signal 0, sorry, which is low frequency. You can see that the frequencies here are very narrow to the middle. That's actually a thing. The Fourier transform is usually computed symmetrically, plus minus, ideally infinity, but if you sample signals, it's plus minus the sample frequency. And then we have a high frequency signal, which is wider apart from the central point. And if you add them, it looks pretty ugly. Maybe it's not so easy to see anymore that it's 2 summed signals. But if you look in the Fourier space, you can nicely see that each signal has its own representation as single peaks. And another operation that is very useful is the convolution. We have already looked at convolution in real space, and that's quite a lot of work to do it. In the Fourier space, once you have transformed the images, you can actually just multiply the kernel in frequency response with the image in frequency space. Multiply them, and then you do the inverse Fourier transform back, and then you have filtered your image. The other way around, personally, I never used it, but it's actually that if you multiply 2 images, it's the convolution in Fourier space. I have never used it, but maybe you can find a use. But it's a mathematical fact that it is like this. Oops, sorry. So looking at noise in Fourier space, you have this image where we add some noise, and then you can see the noisy result here. That would be the same thing as we have the image information Fourier transformed and the noise Fourier transformed. And in this case, I had Gaussian white noise, and white noise means that the noise is represented equally much in all frequencies. So the noise is more or less like a bias in the image that you add on. And what you can see is that if we add that noise to this, you can see the cross here is the central frequency as a 0 frequency. Then you can see when you add noise that the higher frequencies, they are actually hidden in the noise. And this is something we can play with here in this example. And if we want to do a convolution to remove the noise, then we have this, let's see if it's, yeah, it should be loaded. I think I should go back 1 or 2. No, it doesn't want to. Yeah. I think I need to go like that and that. Yeah. So in this example, we have first the noisy image. We compute the Fourier transform of it. Here I use actually the logarithm because otherwise you won't see much. You would only see a white spot in the middle because that's the base level in the image. Now to remove the noise is mainly the information that you have at higher frequencies. We define a filter window, which is just a circle like this. It takes all the frequencies in the middle. Then, as I mentioned before, the convolution is just multiplication of this window, multiply it, and you can see everything around it is 0. And then you have do the inverse Fourier transform, and you have the filtered image. Yes.
You did the 2D Fourier transform?
Yes. Yes.
Okay.
Yes. So I actually do it on this line here. A little bit tricky. The fast Fourier transform. If you have the central frequency, what it provides you is actually an image looking like this. So that is why I need to apply this FFT shift operation, which puts it like this. So we have the 0 frequency in the middle. Otherwise, you would have the positive low frequencies in this side and the negative frequency low frequencies in this side, and then they go towards the high in the middle. So that's why we need to apply this FFT shift operation on the top. The next lines here, I just create my circle. In this case, I set it to be equal to half the frequency space. If I would set here now a very low frequency, you will see that I filter a lot of the noise, but I also lose a lot of information from the image. A lot of sharpness is lost. So that is the effect when I have a low pass filter with too low cut frequency, then you lose also structure information, which you don't want to. I also defined some more, a little bit funny filters. So here is on this line, I have defined a Gauss filter, because you can also do the Fourier transform of the Gaussian window function and have a Gauss filter. Interesting is that the Fourier transform of a Gaussian function is a Gaussian again. So you get the same shape, but it has different width in the Fourier space. So here is the filter window, and I multiply it, and you can see that it's a smoother transition at higher frequency. And that also preserves more of the edges in the image. So maybe I can set here a different value. So maybe 0.1. That will also filter a lot. But again, now I have still pretty good preserved the edges in the image. Going to something extreme would be this one, where, as you can see here, the main information in this image is along the central, so 0 frequency lines. And the idea of this filter is that I'm just filtering those parts. And that would look something like this. So the filter window looking like this. This is a filter which is not very easy to produce in real space, but it can easily be designed in the Fourier space. And the effect of it is, again, I get the filter effect. I get also very much of the high frequencies, but you can see that there is a little bit striped effect, or actually cross-like effects in the resulting image. And that is what is inherited from this filter shape. If I do it a bit more extreme, let's set it to 0.5, I think. So it's more narrow. Then you can see this effect in more. It looks like some kind of textile. And yeah, so that was a little bit of demonstration how you can play around with the Fourier filter. After the break, I'm going to show more about how you can design filters to remove information, very specific information. So see you in 10 minutes about.